Hi, this is Alex from devstories.eu, Python, Cheminformatics, and AI, episode 10 of 22. You wire up a massive three-dimensional graph neural network, feeding it spatial coordinates for every atom and a protein pocket. Then you run a simple gradient-boosted decision tree that only looks at the two-dimensional sketch of the drug. The benchmark finishes, and your cutting-edge spatial model just got beaten by an algorithm from 2 decades ago. The reason your heavy network failed is rooted in how we handle predicting binding affinity. Predicting binding affinity is the computational process of estimating how tightly a small molecule or ligand attaches to a specific protein target. In drug discovery, finding a molecule that binds strongly is the entire goal. To do this, engineers typically take one of two paths. The first is highly complex. You use three-dimensional neural networks like GraphNet or TensorNet. These models ingest the exact bound conformation of the protein-ligand complex. They use message passing layers to learn the precise spatial distances and quantum mechanical features between the atoms of the drug and the atoms of the protein pocket. The second path completely ignores the protein. You drop the spatial coordinates and use a classical two-dimensional model like XGBoost. The input here is just a concatenated vector of molecular fingerprints. You compute structural features from the ligand alone, essentially turning the two-dimensional drawing of the chemical into an array of numbers, and feed that directly into the tree-based model. To see how these approaches compare, researchers run them against standardized test sets. One of the most telling is the Merck FEP benchmark. This dataset mimics a common virtual screening scenario called a congeneric series. In a congeneric series, all the tested ligands share the exact same core chemical scaffold and bind to the exact same site on a single protein target. The only differences between the molecules are small structural variations, like different chemical branches attached to the main core. Here is the key insight. When evaluated on the Merck dataset, the heavy three-dimensional models achieved a correlation score around 0.3. The simple two-dimensional XGBoost model scored significantly higher, reaching 0.45. The computationally cheap decision tree clearly outperformed the advanced graph neural networks. This happens because of what the models are forced to focus on. In a congeneric series, the protein target and the binding pocket do not change. The three-dimensional model spends massive computational resources mapping a spatial environment that remains static across every single test case. Worse, these models are highly sensitive to tiny variations in atomic coordinates. A slight arbitrary shift in how a hydrogen atom is placed during data preparation introduces noise that distracts the graph network. The two-dimensional model succeeds precisely because it is blind to the protein. By only looking at the ligand features, it relies on the only variables that actually change from one test to the next. The decision tree correlates those direct structural variations in the drug to the final binding strength, bypassing the noise of the spatial environment entirely. Heavy three-dimensional models are still highly valuable when you need to generalize across entirely different, unseen protein targets where the pocket geometry is unknown. But when you are optimizing a specific family of drugs for a single known target, feeding constant environmental data into a deep network is inefficient and prone to error. The most powerful predictive tool is often the one that filters out the static environment and models only the variables that change. That is your lot for this one. Catch you next time.